My name is Emily Maggioli. This presentation is part of deliverable 3.4 of Work Package 3, entitled Protection of Hybrid AC-DC Grids, Feasible and Implementable Approaches, part of InnoDC project. The work in this presentation is based on the paper titled Impact Voltage Source Converter-Based HVDC Interconnection on AC Power System Energy Transmission Wide Area Disturbances, which was presented at DPSP 2020 conference. The outline of the presentation is as follows. Point 1 is the context, motivation, and contribution of this work. Point 2 are the concepts in wide area. Point 3 are wide area disturbances and voltage source converters, possible disturbances and/or contribution towards wide area disturbances. Point 4 are challenges in wide area. The main challenges will be listed and explained. Point 5 is the methodology proposed in the paper for studying wide area disturbances on AC transmission networks, considering voltage source converters. The context of this work can be organized in 3 points. The first is legislation and pressures for emission reduction, which have led to an increase in renewable energy adoption and penetration. The other is the use of HVDC technology in transmission networks due to the costs over long-distance transmission that is lower than AC. Finally, the adoption of wide area monitoring systems. There has been an increased interest in adopting the systems for visibility of the system. The motivation for doing this work is to understand the possibility of new network conditions and behavior with the increase of power electronics and renewable energy source integration. These could increase stress on transmission systems due to growing transfers and also an increased risk and vulnerability to blackouts, as the system could be operating outside the originally designed limits due to all of the changes of the elements in the system. The contribution of this work can be summarized in 4 points. It's an overview of the main concepts in wide area, a list of some of the main challenges faced in wide area, a possible list of contribution or effects of voltage source converters in wide area disturbances, and finally a methodology for studying these disturbances. This slide explains the time frame for wide area protection, which lies within 0.1 and 10 seconds, which is within unit protection and SCADA EMS. It's different from unit protection, as it assumes the phenomena after short circuit protection has acted, but also before SCADA comes into place. It focuses on system stability and preventing blackouts. Here we have the 3 main concepts in wide area. One is the phenomena. The other are the systems for acquiring information, WAMS and WAMPAC. And C, we have the protection systems, wide area protection and system integrity protection. Here we have listed the main phenomena in wide area. We'll have the triggering events that lead to disturbance or stressed conditions, and then from that we could have cascaded failures or blackouts. The triggering events can be anything from external threats, weather conditions, hidden failures, operator areas, or even sabotage. The disturbances or stressed conditions are based on the PSRC report and go from voltage instability, voltage excursion, angular instability, considers also possible loss of synchronism, small signal excursions, oscillatory instability, even inter-area oscillations, equipment loading, high power transfers or bottlenecks in the system, phase imbalance, and even cascaded failure tripping. Any of these stressed conditions could lead to blackouts or even cascaded failure, but not necessarily. Here we have WAMS and WAMPAC. WAMS stands for Wide Area Monitoring System, and it consists in acquiring a vision of the system through synchronized measurements technology. This means that all of the measurements made in the system will have a timestamp, so they can be relatable between them. Another information is that these measurements are usually acquired through PMUs, phase measurement units. WAMPAC stands for Wide Area Monitoring, Protection and Control, and considers all the WAMS systems with the additional protection and control functionality. The goal here also is to get the vision of the system, but also disturbance mitigation. Analyzing the protection systems. As mentioned before in the time frame, system integrity protection and wide area protection are different from unit protection. Unit protection is focused on a single element of the system and protection against short circuits, for example, line protection. Whereas SIPs and wide area define a set of actions and control to protect the integrity of the system. These two definitions are very closely related. Basically, wide area protection is the system integrity protection in wide area monitoring systems. Here we have a classification of some of the SIPs. And this can be done in three forms. The first one, system proportion, and this is a classification based on the system impact. It can be local, subsystem, or system-wide. System-wide can mean a whole TSO or even can mean two interconnecting TSOs. The second depends on the size of the SIPs and the proportion of the system impact, going from wide area protection schemes, local area, or safety nets. And finally, the classification can be made based on impact and control principles. And this depends if there have been pre-calculated parameters based on offline studies or not. Here we have listed the main challenges in wide area, and they have been categorized. We have the data management in wide area monitoring, or wide area monitoring, protection, and control. And this is related to collecting, transferring, or communicating the data and analyzing this data. It can be challenges from communication systems, from the collection systems, errors in the measurements, and also being able to analyze the data in terms of storing it and getting information from it. We have system observability through PMU location. There is a cost associated to PMU, but there's also a desire to get the visibility of the system. The challenge is to optimize, is to maximize the amount of information of the system by minimizing the number of PMUs that you have to install to minimize the cost. Another challenge is the coexistence of legacy technology. As a system evolves, you'll have different levels of technology in the system. And this will have an impact on the operation of new technology because there could be an interaction between this and older technology. Another is standards and regulation. These are ever evolving at the moment. And despite all of the regulations currently, they are under discussion and being analyzed as well, where is their application, and if they're relevant and they will require any further detailing. Finally, tooling challenge. In terms of wide area analysis, it requires dynamics. And if you're doing wide area protection studies, you need a tool that allows for the appropriate dynamics, but also for protection modeling. This has historically been done in two different tools. So the challenge is to allow for the appropriate modeling requirements to get comprehensive results. The current slide has a diagram that explains the process for getting to the table, which is in the next slide. Started by categorizing interactions. This has been based on previous work. From this, we have used a categorization of the disturbances, which has been based on the PSRC reports. The combination of these two have led to an analysis of possible stress conditions, which can originate by considering voltage source converters in the network. The table generated is below, as you can see. On the left-hand side, you have the interaction categories, with in the middle an explanation of the impact on protections. Finally, on the right-hand side, you have possible stress conditions. All of the work has been done with focus on studies and impact on protections. In the case of short circuits, increased clearing time could lead to angular instability. For example, if the actuation of protection exceeds the critical clearing time. Also, if the protection does not exceed the fault clearing time but takes longer than expected, for example, if we get a short circuit, and in the case of distance protection, if we expect zone 1 or we get a zone 2 actuation, we could lead to have conditions of, for example, voltage excursions because it takes a bit longer than expected. In the case of protection settings instability, which is closely linked to the above category, longer response time could mean exceeding also the critical clearing time, and this will create instability in the system from voltage, angular, oscillatory. Regarding short circuit ratio, with the increase of short circuit ratio, we could have faster and undamped variations in the network, which could generate voltage excursions, frequency excursions, and also small signal excursions. Finally, harmonics and resonance. This can be due to the introduction of harmonics from converter operation. One of the impacts could be harmonics in the measured signals by the relays, like voltage and current, and this could impact the protection function performance and lead to incorrect operation. In the worst case, it could lead to cascaded failure. Also, another consequence could be the existence of off-nominal frequencies in the system. And this is an additional stress condition that has been proposed. All of these stress conditions list are possibilities, which will then be assessed using the proposed methodology to compare against the expected interactions and the actual results. This table presents some of the mitigation procedures which can be used when faced with some of the disturbances. On the left-hand side, there are a list of system integrity protection system targets, either frequency instability, delayed voltage recovery, and on the right-hand side, you have the actions against these disturbances. The methodology proposed is divided into 3 steps. Step 1, disturbances and interaction. In this point, you identified contribution of voltage source converter towards AC disturbances. This is in the summary table presented in slide 13. Also, a consideration to take into this point is network conditions, either high loading or maintenance. For example, if there are any of the lines or any of the elements of the system that are under maintenance at a time. As this has been found in many of blackout conditions, that actually parts of the system were in maintenance, so the system was not in the original expected state, which also led to pressures occurring elsewhere in the system and then having wide area disturbances. Phase 2 consists in the assessment of the interactions and disturbances. For this, we'll compare the results in the table with the expectations. And this means recreating any of the disturbances known. This has to be done considering dynamic simulation tools and is also used to assess the impact on the protection system. The first step is to be able to recreate the disturbance and then add elements of the system in, or do the whole system analysis if possible. Step 3, mitigation requirements and procedure. Once the disturbance has been recreated, a set of mitigation procedures or requirements can be proposed and assessed at this point using the same simulation as step 2. The impact of this methodology is to be able to understand the impact of wide area disturbances on protection, considering voltage source converters. So by being able to compare if the expectations with the actual results in the simulation, we'll be better understand the contribution of voltage source converters towards wide area disturbances, particularly the interest of this work, the impact on protection performance. Thank you for your time.